Everyone's favorite topic, limits, coming back. Let's not dilly-dally. Remember this? Remember this? Remember that? Told you should memorize that. And not just that. Not just that. I asked you, like, hey, maybe get this one down too. Of some number. Huh? It's equal to 1 as well. Just as long as the argument matches with the denominator, you're good to go. And I also showed you that the reciprocal of 1 is still 1, right? It's still equal to itself. So even if you flip it over, it's still 1. Come on now. All right. And that's going to be the nature of our game. Here's the game. We want to create these. Just want to create them. Now the A's are going to be all kinds of different numbers. Let's try our first one. Let's go real simple. Limit, as x tends towards 0, of sine of 3x over x. Cool. We can't evaluate that. You know why? 3 of x does not equal x. It's got to be the same thing top and bottom. So here it comes. We're gonna magically give it stuff. We're just gonna give it. What does the denominator need? What needs to be right here for us to call it 1? A 3. So what we're gonna do is we're just gonna multiply by frickin' 1 over here. Just multiply 3 over 3. Now these numbers don't have to sit at the frickin' end. I'm gonna take this 3 and pop it all the way to the frickin' outside. This one, I'm just going to set it right there. Because it doesn't matter. Multiplication's commutative. It goes wherever the frick you want it to. Limits have a rule with constants, with coefficients. Yank that shit out to the front. We put it wherever the hell we want to. Don't be tied into the fact it has to sit there. Multiplication is dope that way. It's division and subtraction that suck. So let's use those rules. So I'm going to bring them in. And go, all right, let's do this. We got the limit as x tends. Let's give myself a little bit more space there. My equal sign. As x tends towards 0, and we got our sine of 3x over x. And we're going to take that bottom 3, we're going to put it right here. Now this top 3's got to go somewhere. Like I said, I'm going to yank it out to the front and just multiply. So does this shit and this shit match now? Do these two match now? 3x and 3x, they match, so the answer inside has got to be 1. Hence, we're left with that 3 that's on the outside times 1, which is equal to 3. This is our game. Let's try another. Let's get a little tougher now. Limit as x goes to 0, let's go sine of, let's go with 4x over 5x. Tough stuff. Like, well, I got to use this thing from up here and go, well, they got to match, huh? They got to match, but I don't think they match right now. I don't think 4x is the same thing as 5x. So what I'm going to do is I'm going to use the same idea with that multiplication down here, and just looking at this 5 and going, nah, that thing's not a 4. I'm going to take you and yank you out to the other side. Except it's not a 5. It's actually a 1/5. It's actually a 1/5. So when we yank it out, I'm going to yank that 5 all the way to the outside. And it's going to leave us with sine of 4x just over x. So this guy here traveled over here. But since it was in the denominator, it's not 5. It's 1/5, right? Dividing by 5 is the same thing as multiplying by 1/5. Now we can play the same game we did before. But we're trying to match them up. We're like 4x and x. Well, dang, I can't call it 1 yet. We're trying to get a 4 down there. So we're going to take that and go, all right, well, let's just multiply by 4 over 4. Well, let's take this 4 and we'll bring it out and bring that to the numerator. We're going to take this 4 and bring it inside there. You're starting to see the trick. You're starting to see it. There's a pattern in here. And oh, here comes that 4 from the bottom. Now we look and we're like, hey, look, the argument and the denominator match. So the limit is x tends towards 0, sine of 4x over 4x is actually just equal to 1. So right inside of here, that's just 1, and it just leaves us with that 4 over 5 being multiplied. So our answer is 4/5. Simple, right? You got this thing all day long. No issues whatsoever, huh? Huh? You probably catch the pattern, don't you? Catch the pattern? What was this answer in the first one? 3. What was this one's answer? 4/5. So you think you got the pattern? Let's find out. Actually, I'm just being a jerk. Just being a jerk. Saying don't try and necessarily find a pattern. I double check. Uh-oh. The game changed. It's not just a sine of x up top and an x down below. Huh. Shoot. What are we going to do here? Oh, I know what we could do. Let's break it up into pieces. Let's call this as the limit as x tends towards 0. And let's call this sine of x over 1 times 1 over sine of pi x. Oh, there we go. Now, let's use some limit laws. Let's bring it in. Let's bring in them limit laws. Shoot. Okay, cool. Dang. Well, let's just look at our first one. Man, I wish there was an x there. Because then we could just call it 1. And man, we need an x there. We need an x up top too. Shoot. And then we'd be on our way to calling it 1. We'd be on our way. Dang, I wish there was an x top and bottom. Wish there was something we could do. Yeah, just multiply by 1. And put that x there. And put that x there. Since you have the ability to pause, I'm now going to just bring it over there so I don't have to rewrite this. So now we have the x's. Shoot, this one's done. That one's done. We can just call this 1 times our limit as x tends towards 0 of x over sine of pi x. What does this one need? Because we don't match. We got a pi x, we got an x. Shoot, now it's just a constant. Now it's just a number. You know that 3 and some change that pi is? We're going to multiply by pi over pi. So that pi can go right there to where it's going to match, and this one's going to go out to the front. So we're going to get 1 over pi times the limit as x tends towards 0 of pi x over sine of pi x, which is equal to 1 over pi times 1, or just 1 over pi. I thought you saw the pattern. It doesn't always work like that, though. It doesn't always work like that. I have some jacked up ones for you. I'm just going to let you say, like, I like this problem. I'm not going to solve them. I'll leave it for you. I'll leave it for you. You know, maybe do it or don't. Go figure out what that is. Go show what that is. All right. Next one. We're out of here. We're going to start seeing some games like this. Some Leibniz notation. Maybe we go find the 29th derivative on sine of x. You're like, what the frick just happened? Leibniz notation, 29th derivative. Or maybe we wanted to be like, oh, we want to take the 17th derivative. So on the d up top, you put the 17, and on the x, you put the 17. Telling you how many derivatives to take. And you're like, dude, I don't want to take 17 derivatives. And your asshole teacher might ask you to do 171 frickin' derivatives. There might be a pattern. You know what I mean? There might be some sort of pattern. So let's just go aside. I'm just going to say, all right, f of x is equal to sine of x. This is what we call the 0th derivative. We're not taking any frickin' derivatives here yet. So this is 0. Let's go take our first derivative. See if we catch a pattern. And that's going to be cosine of x. On our second derivative, we're going to find out we get negative sine of x. On our third derivative, we're going to find out that we get negative cosine of x. On our fourth derivative, like the Roman numerals, makes me feel fancy, we go back to sine of x. What do you think is going to happen when you go to your fifth? We're going to get cosine of x, and the pattern repeats. And the pattern just repeats and will go on forever. So every four, we're going to find out that this pattern repeats. So you only really need to look at these four. Now I'm going to do yours. 171. And you're like, which one's it going to be? Where's it going to end? And I'm going to show you a quick trick. Shh, don't tell anybody I showed you this. How many options are there? There's four. There's four options. So we're going to take whatever we have, that 171, and we're going to divide it by 4. And whatever the remainder is going to be our answer. What? Long division, dude. Long division. How many times does 4 go into 1? It doesn't. How many times does 4 go into 17? 4 times. Don't give a shit, though. That's the 16. We subtract 1. Drop it down. How many times does 4 go into 11? Twice. I don't care. I don't give a shit about the number up top. The only number I care about is the remainder. Saying that this would have gone around in this pattern, we would have gone all the way up to I don't know, the 168th derivative, because 4 times 42 is 168, and then you need to go 3 more of them to get there. So it's this frickin' remainder here is telling you that the answer must be this one or negative cosine. I'm saying I never told you. See.